Okay, so picking up exactly where we left off in the same notebook, we are going to build this simulation. Okay, so the first thing I need to do in order to start, or build the animation, I should say, the first thing you need to do is import some animation functionality. So we'll say from matplotlib.animation, we're going to import func animation. Okay. And then because I want it within my animation, I want some subplots. I need to import some extra functionality. So import matplotlib.gridSpec, and I'll import that as grid. And the last thing I need, well, not the last thing, but the next thing I need to do here is change the plotting mode from my notebook. So that will be a %, and then matplotlib notebook. Okay, so they're just some of the extra imports and settings we need to set if we want to do some animation. So we'll execute that. And next we can move on down and set some animation parameters. All right, so if you've taken my multi-degree of freedom structural dynamics course, you'll have covered some of this already, because we're using the same patterns that we use within that course to generate the animations of our multi-story structural oscillations. So we'll just call this animation parameters. All right, so the animation length, how long do we want our animation length to be? Right now, again, depending on your hardware, if you try and do a really long simulation, or a really long animation, you should be able to do it. It's fine. It'll just take a long time, right? So I think I did a 100-second animation, and it took a good few minutes to generate that animation. So for the purposes of developing code here, I'm just going to set that to 10 seconds of animation. Now, what is the frame rate? What frame rate do you want your animation to run at? Depending, if you have a high frame rate, your animation will be really smooth, it'll look great. If you have a low frame rate, it's going to look really choppy. So a reasonable frame rate would be, let's say, 12. And again, you can, if you want to reduce the amount of time it takes to generate an animation, reducing the frame rate also helps, right? So you could you'd use anything from 5 to 10 to 20 frames per second, but we're going for 12 frames per second. Next, I'm going to define a plot interval. Right, the plot interval here is going to be the time between frames, okay, which is obviously just 1 over the frame rate. Then I want the data interval, right? So that's just going to be the plot interval divided by del time, the time step. This is basically how many data points have passed between each frame. Okay, so it's going to be plot interval divided by my time step. So that's all of my animation parameters set up. I want to add an additional parameter here called def scale, or deflection scale. And I'm going to set that equal to 500, because I'm going to have to scale the deflection of my bridge by, in this case, 500, in order for us to be able to see it and for it to generate a useful looking animation. All right, so we can execute that cell to define all of those parameters. Right, so the next thing we're going to do is define our axes. We'll define our figure and our set of axes. Now, you'll have seen on the very first video within this project where I was sort of showing a preview of the final animation we'd end up with. There's going to be 2 subplots. The top one is going to be an aerial or top-down view of the bridge deck, showing pedestrians essentially walking across the bridge. And then the one below that, the plot below that, is going to be a side-on view, if you like, of the bridge oscillating up and down. So this is where we're going to set that up. So we'll say fig and AX1, let me see, let's put that inside a set of parentheses. AX1, AX2 is going to equal plt.subplots, and we're going to say n rows is going to equal 2 and n cols is going to equal 1. And then we'll pass in a parameter fig size, it's all lowercase, fig size equal to 10, 5. Okay, so we're defining our figure and our subplots here. So next we can control the ratio of heights between the subplots, right, by using GS. So we're using grid spec and assigning it GS, right? So we can say GS is equal to grid spec. Okay, that was the thing we imported at the start of this lecture. So from grid spec, we will call grid spec, capital G, capital S, and then the parameters are going to be 2, 1, and then the height ratios. And so because we are going to have these two subplots can have the same heights, essentially. They can have equal heights. We can just pass in 1 and 1. All right, and then we're just assigning AX1 to be plt.subplot GS0, and AX2 is subplot 1. Okay, so that's our subplots set up. Next, we are going to, the one other thing we want to do here in the setup is we want to set the x-axis and the y-axis for our subplot, because this is a plan view, an aerial view of a 2D plane, and the x-axis and the y-axis should have the same scale for that particular view. We want to set the aspect. So we'll say AX1.set aspect, and we'll pass in the string equal, and we'll say adjustable equal to box. There's a lot of fairly, there's a lot of setup code for this, and a lot of it is fairly arbitrary. You've got to kind of dig into the docs to sort of remind yourself what all these different options do for you. But broadly speaking, this line of code is basically ensuring that the x and y axes have the same scale for our first subplot AX1. That was the aerial view. All right, more setup. We got to set our axis limits, right? So I'm setting the axis limits for the first subplot. So the x-axis limit is going to be 0 up to L, the span of the beam. And the y-axis limit, I'm going to set it as -3 and 3. So I'm going to assume my deck is 6 meters wide. So that's the first set of limits we can define. Next, I'm going to set the axis limits for the bottom plot, which was the side view of my bridge oscillating up and down. So the x-axis limits can be the same. They're going to be 0 on the bridge span. And then the y limit, you got to think about that. What's the y limit got to be? Well, the y, in the y direction, we're viewing the bridge vibrating up and down. So the y limit, I'll just define it here. I'll say y lim 2 is going to equal, what's it going to equal? The max value of res crowd, right? The max value of the response generated by the crowd. But remember, we're multiplying all of those displacements by a scale factor so that we can see them. Okay, so def scale. And now we can go ahead and assign those limits, those x and y limits, for the second set of axes. And then we're just going to set, in the usual way, some housekeeping, so setting titles and axis labels. So once all that initial setup is done, let me run that when you'll see, well, that's what you get. So that's our initial setup done, right? So now what we want to do is plot the initial state of everything, right? Everything's position at time 0. And then in an animation loop a little bit later, we're going to go in and update various different positions based on what the data is for that particular time in the animation. But the first port of call is to define the initial state of everything, right? So let me see, what have we got here? We've an issue here, height ratios. What have I done there? That's supposed, instead of height ratios like this, it's supposed to be, let me go back up. It's supposed to be height underscore ratios with a lowercase. So let's try that again. Okay, excellent. So now this is what we get, right? We got our nice axis labels, we got our titles. So we're good to go. We're good to start plotting the original or initial state of everything onto this set of axes. So we're going to focus initially on the pedestrians in that top subplot. So that's our pedestrians as we view them from above, walking from left to right across our bridge. So I'm going to have to define a container to hold the definition of all of these pedestrians. So I'll say that's equal to an empty list. And then I'm going to step through or loop through each pedestrian, define a Y position, a Y starting position for the pedestrian, and then add them to the plot and then add them to our list so that we can update them later on. So let's loop through each of our pedestrians. So usual way, for I in np.arange n. All right, what's the first thing I want? Well, I want to know where across the width of the deck are they, and I can just, because there's no interaction between pedestrians, I can just randomly assign. It doesn't really matter if they overlap with each other, so I'm just going to randomly assign np.random. We saw this earlier. From a uniform distribution, I'm going to extract a value with a lower limit of -2.5, let's say, an upper limit, or let me see, it should say high. The higher limit is 2.5, and the size, I only want one sample value, so size can equal 1 for this current pedestrian. And then now I can add them directly to the plot. So I can say ped top. Now don't forget that comma, right? You need that comma in there. So ped top is equal to ax1.plot, and I'm plotting them onto the graph, and their x position will be 0 at time t equal to 0. Their y position can be the random value I just determined. we're going to use a circle to visualize them. Now I want to set a marker edge color to be black. So black is K, and I want to set a marker size. And the marker size is going to be 10. You need to play around with these values to see what works. Obviously I've played around with these to see that 10 works quite well. And now that I've defined that pedestrian, I need to add them to my list of pedestrians so I can access them later. So I'll say top ped list dot append, and I'm appending in ped top. Okay, so that's my initial pedestrian. So if I run that now, you will see a whole load of circles added to, well, we'll only see half of the circles because they're added to the 0 position here. So let's try it. Excellent. So there's all our pedestrians on the start line, ready to go. Okay, so now let me come down and define the pedestrians as they appear down here in this plot. So this is going to be a plot of the bridge, but I also want to visualize a side profile of my pedestrians as they walk from left to right. So we got to define them in for this plot down here as well. All right, so we're basically repeating, right? So I'm going to copy this and drop it in here. We'll dispense with the note. And we'll call that BTM for bottom ped list. Okay, let's just give ourselves a bit more space here. And we can cycle through each of our pedestrians again. This time we're adding a pedestrian to the list. So the pedestrian, again, don't forget that comma, is equal to adding it to the second plot this time. So ax2.plot. And okay, so what's the x position? I just want a line, right? So a vertical line to indicate the pedestrian. So the x coordinates at time 0 are going to be 0 and 0. The y coordinates of this pedestrian are going to be 0, okay? And then what's the height of the pedestrian? We just need some height that is that's going to appear on our graph. Now again, I've played around with the numbers, and it turns out that if I set the height of the pedestrian to be 0.6 times the y limit that we specified, and that looks about right. And then we just got to save this pedestrian. So that is all of our pedestrians defined for the top and bottom. Next, what I want to do is define the initial state of the beam in the bottom plot. So I want to plot the beam, so I need a series of x values. So that's just going to be np.arange going from 0 in step, or up to L plus 1 in steps of 1. Okay, it's just going to be a series of values that I can plot indicating the bridge. Okay, so we now want the mode shape. So we'll say phi vals. So the mode shape value corresponding to each of those x positions. So that's just going to be np.sine of pi times x vals over L. And now we want the beam displacement, right? So the beam displacement at time t equal to 0 is just going to be, it's going to be 0, right? So it's going to be a horizontal line. So I can just say, 0 times my phi vals. Okay. And of course, if the displacement was some non-zero value, remember the displacements we have are the displacements at the mid-span. And so I can get the displacement at any other point in the beam just using the mode shape, which is this guy here. So if I had a mid-span displacement of 10, well then to get the displacement at every other position along the beam, I would just take that value of 10 and scale it by the correct mode shape value for that other location in the beam. Okay, sort of standard modal analysis. Okay, so now we can just add a couple of lines to that bottom plot. So we'll define an axis line here. Again, comma, axis line is equal to ax2 dot plot, and we're going to say x vals and then beam disp. So it's obviously going to be these beam disp values that we're going to update within our animation loop. And so that's actually just going to be an axis line. That's never going to change. I always want a black line indicating the original position of the beam. But then I want a deflected line, and this is the one that's going to indicate the beam deflection. So that's going to be ax2.plot. It's actually going to be, it's going to start off the very same, but I'll make it red. All right, so let's just run that. Before I run that, I want to zero out everything on my set of plots. So I'll start with a fresh set of plots and then run this. And we can see there we have it. Now you might be able to see that on the video and you might not. There's very faintly just a vertical line here. So that's going to indicate a pedestrian essentially starting, corresponding to these guys here, starting and ready to start walking across. So now we've got that done, we can build our animation function. This is the function that's going to do the hard work for us, right? This is the function that updates the various different pieces of data from in here on every frame of our animation. So this is a function to animate the plot objects. So we'll say def, we're going to call it animate, and it takes a parameter I. We're going to say frame is equal to, I want the frame number, so that's going to be, let me see, I times, that's an iterator that counts up every time the function is called. So I times the data interval. Remember, that was the number of data points between each of our frames. So the current frame is going to be I times the data interval. And then what's the sim time? What's the time within the simulation for the current frame? Well, that's going to be from frame, we're going to index in, or from time, we're going to index into the value located at F or M, the current frame. Okay. Next up, we're going to update the pedestrian positions in the top plot for the current frame. Okay, so this is how it goes, right? This gets called for every frame. And so what we've done is we've said, okay, every time you call this function, what is the index within our larger data structure? What's the index in our data structures for the current frame? And that's this guy here. And now what we're going to do is basically update the various bits of data by accessing the value within our data structures located at frame, exactly as we've done here for time. So we've reached into our large time vector and we've pulled out the current value for the current frame. Okay, so let's crack on here. So we're updating the pedestrian positions in the top plot. So let's say for each pedestrian, for I in np.arange n, we're only going to update the pedestrian's position if the simulation time for the current frame is greater than their start time, the time that that person started walking, and less than the time it took them to get across the bridge, right? So essentially, we're only going to update their position if they're still on the bridge. And the way we do that check is we say if sim time is greater than, remember, we saved all the start times for each pedestrian. So if it's greater than the start time for the current pedestrian and it's less than the time it took them to get off the bridge. So that was going to be whatever their start time was, plus the time it took them to get over the bridge. And that was just going to be the span of the bridge divided by their walking velocity. All right. So if we've satisfied that condition, then come in and update the pedestrian. So to update the pedestrian, we've got to grab a hold of them first. So we'll say PT for the pedestrian in the top plot is equal to reaching into that array of pedestrians we saved, or that list of pedestrians we saved earlier. So reaching in to grab the current pedestrian, we're going to calculate what that pedestrian's position should be. So the position is going to be whatever the current sim time is minus the start time for that pedestrian, right? So that's basically a time times their velocity, right? Right, so a time times a velocity gives you a distance. So that's meters. That's their position. That's how far along the bridge they've moved for the current frame. And now all we have to do is update their position, right? So pt dot set x data. That's let me see, x data, all lowercase. And what are we setting it to? The current position we just calculated, right? So that updates the x position for each pedestrian, provided that they're still on the bridge in the current simulation frame. So let's do another one. Let's update the beam deflection shape, or the beam deflected shape for the current frame. Okay, so how do we do this? Well, we're going to reach in directly and say def line, right? So that's that guy that we defined there. So we're saying, calling him, and we're saying def line dot set, not x data or y data, just set data. This allows us to update the x and y's at the same time. Now we could just update the y's now that I think about it. The way I've written this is to just say set data. So we've got to pass it the x values, which don't change, they stay the same. But what does change? The y values. So it's going to be minus the deflection scale times, let me build this up the other way actually. What's it going to be? Well, what's the deflection at mid-span? It's res crowd for the current frame. It's res crowd frame. Now we've got to map that deflection over to every one of the x positions. How do we do that? Well, we just multiply it by the mode shape values, right? So phi vals. So that takes that maximum mid-span deflection and maps it to every other value along every other position along our beam, and then we have to scale it. Right, because it's going to be too small to see, almost certainly. So multiply it by def scale, and then take the negative of it because you want the deflection to be downwards. And that's it. That's the deflection updated for our beam for every frame. And then the last thing we got to do is update the positions of our pedestrians in that bottom plot, that side view of our pedestrians as they walk across the structure. So again, looping through each of our pedestrians and only updating them if they happen to be still on the bridge. We're going to define or reach in and grab the current pedestrian. We'll just define them as PB, and that's coming from bottom ped list. Okay, so what do we want? First of all, we want the position. Well, the position is going to be the same as it was in the top plot. Now I want to do one extra thing here. I want the height of the pedestrian when viewed from the side. I want their height to be changing in time with their forcing frequency, right, with their ground reaction force, so that you can really visually you can really tie together you can see the force or the frequency of the force that's being imposed on the structure, and then you can also at the same time see the response of the structure. So we're going to scale the height of the pedestrian, and we're going to use the current value of their ground reaction force in order to get that height. So let's say the height of the pedestrian, it has a minimum value, right? Let's say the minimum is 0.1. But let's add to that another 0.1. But let's scale that 0.1 by the current value of their ground reaction force, right? So let me see, ground reaction force for the current pedestrian, for the current frame. So we're scaling it by that, but we don't want to scale it by the absolute value. We'd like to normalize this by this force value, by the maximum possible force value for this pedestrian. So we'll say max crowd force I and let me see, all, so for the pedestrian I, but all of their values. So what's that doing? That's basically saying the height of the pedestrian is going to be, it's going to go, well, let me see, this is going to be a factor that essentially goes up and down, up and down, up and down, okay, between 0 and 1, okay, based on the forcing function, right, the pedestrian ground reaction force. So what you're essentially doing is you're scaling this value of 0.1 by a value between 0 and 1 that's going to oscillate or rise up and down in time with the ground reaction force. And so you're going to, your height is going to go from 0.1 up to 0.1 plus 0.1, which is 0.2, back down to 0.1 again. But it's going to be going up and down in time with the ground reaction force for the individual pedestrian in question. Now all we got to do is update the pedestrian. So let me see, let's go back here. So let's say pb.set data, and what are we setting? We're going to update the x positions. So pause, and update the y positions to be 0, 0, and h. All right, and that should be it. Now we can just return out of the bottom of this animation function, and we're done. Okay, so that's the function that basically updates our plot for each animation frame. No matter what you're animating, it's the same basic idea. If you're animating within matplotlib, you set up your set of axes, right, whatever way you want, depending on what you're animating. You add the initial state of everything in your set of axes, right? Your people, your bridge, whatever you're animating. And then you build a function, which is this guy here, that's going to update all of the different things within your animation for each animation frame. And that updating involves essentially reaching into your data, right, that you're using to build the animation, extracting the values for the current animation frame, and then updating using set data, updating the various different elements of your plot. And then all you got to do, that's the hard part done. Then like he says that, and then he gets an error. Let me see. Once you've got that done, we're going to write another little function that calls this function. But let me see what the issue was here. pb.setData. What did I do wrong here? Okay, I see what's wrong. We've got one, after a lot of staring at it, we've got one bracket too many. Okay, so let me see. Should that work? That should work. So 0.1 plus 0.1 times all of this, which is just one number divided by another number. I don't know why that return has turned red. Let's try this again. Retype return. Okay, let's try that. Excellent. Okay, so the function is working correctly now. All right, so we just had a typo. We had one extra bracket in line 21 here. Okay, so now we're at a point where we can actually generate our animation. Now, word of warning before you actually, well, I'll write the code, then I'll give you a word of warning, right? So this is going to be the same code every single time. Well, it is for me at least every time I do an animation. Let me just get a note in here. Okay, function to generate the animation, right? So I'm going to say my animation is equal to, this is where we call that func animation that we imported at the very top. Func animation, right, we're going to pass into that fig, right? There's going to be a lot of arguments here, or parameters. I'm going to go new line for each one. This is the animate function, okay? This is the guy that updates every time. The function that we call to update our animation. We're going to call frames, right? So how many frames have we got? Well, that's going to equal an integer, and it's going to be 1 plus, in brackets, the animation length divided by the plot interval. Get rid of that typo. Plot interval. Okay, next we can have our interval, which is just going to be the interval, the time between frames in milliseconds, right? So that was just going to be plot interval times 1,000. And then we have another one, which is one of these bizarre ones called blit equal to true. I think this has something to do with only updating, only redrawing things that have changed on subsequent frames. But I would say, if you really want to know what it is in great detail, refer to the docs, because I honestly cannot remember. So repeat is going to be true, and that just does the thing repeat itself. All right, so that is the function call that actually generates our animation for us. And the last thing I'll do is say plt.show. That's the second last thing I'll do. The actual last thing I'll do here is say my animation. I'll generate a GIF file, right? So I'll say my animation.save, and then I'm going to pass in a name. We'll just call it bridge response.gif. Okay, excellent. That's it. When we execute this cell, it will generate our animation and then try and generate a GIF file, so we'd save it to a GIF file. Now, the word of warning which I was going to give you was, depending on how long your simulation is and how many frames per second you've decided that you want to use, this could take quite a long time to animate or to generate. Okay, so what I would say is, to make sure the thing runs correctly, I'd start off by going back up here, and instead of looking for a 30-minute simulation window, I'm going to change that back down to a 10-minute simulation window. In fact, yeah, 10 will do. And that way I'm going to run this from top to bottom again, make sure it's working, it's generating an animation, and then at a later date, or once you know it's working, you can then set that back to 30 minutes, 60 minutes, whatever you want. Set your code running, walk away, go make a cup of tea, have your dinner, come back, and then it should all be done. But for the purposes of code development and debugging, set that window to a small number first. Okay, so let me run this from top to bottom and see if it all works. Okay, so we ran into a bit of an error because I have a typo. That should not be frame, it should be frames. Okay, so we knew everything ran all the way down to this last cell, so I won't run everything from the top again. I'll just run this last cell. Okay, what have we got now? Another typo. What's this one? Index out of range. Okay, so after some debugging, I have worked out what the issue was. The problem was when we defined our data interval, this is a sporadic error, so you don't always hit it. It depends on the animation length. It depends on the combination of these parameters, basically. But when we plotted, or when we defined our data interval previously, if I just print it out here, what you end up with is a data interval of 16.67. Now that's no good. That's essentially, we need an integer, basically, because this is we're plotting an element every data interval point, right? So what that means is every 16th or every 17th point. So the way to solve that is to just force it to be an integer. Okay, so now what we're saying is our data interval is 16 instead of 16.6666. Okay, so when we add that little fix and work all the way down and basically just run the code all the way down, we end up with everything working fine, and you end up with your simulation. So you've got your simulation, or your animation I should say, playing back now. Now it's not playing back at full speed, and this is what you're going to find typically when you try and play an animation within your Jupyter notebook. It'll be sluggish, it'll be slow. And so what I find is really good is, after you've generated your animation, what you're going to end up doing is saving out a GIF file. Go to your file explorer, wherever you've got this notebook saved, and then drag that GIF back into your cell here. So change the cell to a markdown cell. Okay, so either in the drop down here, set it to markdown, or within the cell, hit escape and M, makes it a markdown cell. Drag your GIF back into the file, and you'll see it. So that's what I'll do next. Actually, before I do that, let me go back up here and let me stop that. Go back down, and then we'll just drag our GIF file in here. Okay, there we have it. So we know it's working. Now we've only simulated the first 10 seconds of this thing, right? So you can see the person's going along there. And then, so you get the idea of what's happening, and the simulation repeats itself. It starts all over again. So now that we know everything is working, the thing to do now is to go back up and increase the simulation length. Okay, so that would mean going back up to here and increasing our animation length. So maybe simulating something like 100 seconds or whatever you want. Now obviously it's going to take longer, so you need to go away and do something else. You're not going to stare at your screen because it'll take a while. But change your animation length, run the thing again, and when you come back then you should have a file within your folder, which is a GIF file with your full simulation. Now it could be quite a big file depending on how long your simulation runs for. So again, this is kind of a sensible thing to do here is actually to not try and simulate the full or animate the full simulation. The thing is to try and, because all you're trying to do is communicate what's happening, right? So you could animate a small subsection within your larger simulation and get the same message across without having to animate the full thing. So I'm going to animate a longer section of this and come back when it's done. Okay, so here we are back again. So I ran my code from top to bottom, so it randomized the pedestrians again. So we've got our pedestrians moving across the bridge here, and we can see a plan view of them here, and we can see they're moving across here, and obviously the height here is corresponding to their ground reaction force. So again, it's a nice little animation. It really gets across the idea of what's actually happening here. In terms of our bridge, we can see obviously we've got a static deflection, and then there's an oscillation overlaid on top of that static deflection. And that's really all there is to it. You can sit and watch this for as long as you like, but you get the idea, right? And obviously when they get to the far side of the bridge, they stop walking because we've stopped updating their position because now they're off the bridge. So hopefully you found that helpful. I think it's a nice little technique to be able to animate, particularly when you're working with structural dynamics. It's kind of nice to be able to animate things so you can visualize them. So yeah, there's not really much else we can say about that. So at this point, it's worth just making a few comments just to wrap up our project here. So let's review the limitations of the simulation, right? So we've relied pretty heavily on superposition in our analysis. Now, this allows us to calculate the response generated by each person individually, ignoring interaction between pedestrians and between each pedestrian and the bridge. So there's no human structure interaction. Now, in many cases, this is going to be acceptable. For example, only when we're dealing with large lateral oscillations. Remember, we're dealing with vertical oscillations here. But if you're dealing with large lateral oscillations, that's when you're likely to see significant feedback between the walking pedestrians and the structure that they're walking on, and there's your classic Millennium Bridge example for that. So for vertical vibration assessment, without any interaction modeling, what we've done is actually quite acceptable. Now, we've also ignored the mass effect of pedestrians on the bridge, based on the assumption that it was going to be small compared to the bridge mass, and so it wasn't going to have a significant effect. Now, even if you do need to take into account the distribution of pedestrian mass across the bridge, that's pretty easy to do. And it's going to have a predictable outcome, right? It's going to increase the mass and so reduce the natural frequency of the structure. And so that might be conservative or non-conservative, depending on where your bridge frequency is in relation to your average forcing frequency for your crowd. So unless you're attempting to generate a really, really exceptionally accurate simulation, the type of crowd-induced vibration modeling that we've done here is pretty good, actually. It's going to capture quite a lot of the realistic scenarios that you're likely to face. Now, at the very least, it's going to be sufficient to highlight potential serviceability problems, right? So potential issues you might have with the vibration of your structure in service. Now, this is particularly the case when we consider all of the other additional sources of uncertainty that kind of creep into our modeling. So if you think about it, like, how critical is it that we're not capturing some of the effects that I've talked about? Some of the interaction effects, some of the traffic effects. Is it really that critical? Because if you really think about it, there's likely to be an awful lot more sources of more significant inaccuracy within your simulation. And so the inaccuracies that we have introduced through simplifying our crowd flow behavior and simplifying some of the dynamics around interaction, it's not likely to have a significant impact when weighed against other potential sources of inaccuracy. Now, I've made this other point a few times, right? So I've said that another big simplification is our bridge model. It was just a simple beam. And, you know, as I've said, this might appear a significant drawback, but in order to generalize everything that we've done here to a more complex structure, all you need are your modal properties, right? Your modal frequencies and your mode shapes. That's all you need. And you can take this exact approach and map it onto more complex structures. And this is really where the power of modal analysis comes in, because it allows us to reduce the dynamic behavior of complex structures down to the dynamics of a series of single degree of freedom systems. Then those single degree of freedom responses can be mapped back onto the different locations in the structure, exactly the same way we've mapped the response at the mid-span here back to all of the other, because it's all of these other responses at every other location is just a scaled version of the mid-span response, where the scale factor is the mode shape value. All right, so if that's it basically. So if this has given you an appetite for a deeper dive into structural dynamics, you can find details of my other structural dynamics courses on degreetutors.com. So that's it for this one. Hope you found it helpful, and I'll see you on another project or tutorial or course at some point, hopefully in the not too distant future.